Hey guys, so in this video I'll be showing a very short debugging session I hope on how I debugged my ray tracing sample app from what we see here. So this is the deer which is not textured properly. All the geometry is correct but the texturing is wrong. So what should be the goal? How should it actually look like? Uh, It should look like this one. So I'm using the same GLTF model, which means that the vertex buffers, index buffers, materials, textures, everything is same. So both the pipelines should have the same output. So this Hello World is a simple VSPS, I mean vertex shader and pixel shader, and that pipeline has been there around for the last time maybe 10, 20, 15, 20 years. It's pretty old and it is even now it's widely used, but it's old. Ray tracing is pretty new. I think it was started gaining popularity in the last 5 years, and right now games use a combination of vertex shader, pixel shader, mesh shader, and ray tracing. So, so we need to debug what's happening here because the texturing is all wrong. So let's deep dive. Let's dive into pics and get a capture and see what is going wrong. So ray tracing, okay, next and launch, and I got a pix output, pix capture. Pix tool has helped me learn a lot because in addition to just debugging, you can actually see how an app is rendering stuff. So if you don't know what dispatch arrays does or how the dispatch array works, you can just click on dispatch array and examine the pipeline state here. So the root signature, we all know it's a common concept of DX12. You know we have the root signature, and I bound some stuff. We can see that here. And then the pipeline state of ray tracing is very different. It doesn't have the usual rasterizer state, blend state, etc. because everything is done in the shaders. So as you can see in vertex shader, pixel shader, we'll have the rasterizer state, the depth stencil state, etc. And in ray tracing, we don't need that because we shoot a ray and then we know the depth where it hit and it manages so many things in the shaders and the whole pipeline is different. When I say the whole pipeline is different, here we have the shader tables. So the whole geometry of the scene is there in the BLAS, TLAS, and the shaders are here. So it's very different from rasterization. So what are the shader tables? We have a region where we shoot a ray into the acceleration structures, and then the ray can either miss all the geometry, go into the miss table, or hit one of the geometry and invoke one of the hit group shaders. So in my setup, I just have okay, analysis. Start the analysis to look at the shaders. My setup, yeah, if you look at my shader, I just have one region shader, a closest hit shader, which is a hit group. So if you hit the deer, the closest hit shader will get invoked, or else you'll get the miss shader. In my miss shader does nothing because my payload color is initialized with the ray direction. I added this while debugging when nothing is visible on the screen just to see if the rays are shooting correctly. But anyway, yeah, now I debug that the rays are shooting correctly, and what do we see now? We see this one. So we need to debug why the texturing is going wrong. Before that, this is my model view projection matrix. This I'm using this matrix uh, to change the direction of the rays. In if you see here in my ray generation shader in generate camera rays, I use the model view projection matrix. Sorry, it's this matrix consists of a ton of things. I don't know why it is not being shown here, but anyway, I can show it in the code. It has MVP matrix, which is model view projection matrix, view projection matrix, everything. Here we actually interestingly use a view projection inverse matrix because um, the the start the starting point is the screen, and you need to calculate the direction of the ray from the screen starting point to the camera, towards the camera. It's kind of reverse what we see in rasterization. But anyway, let's not deep dive into here. Let's deep dive into what's going wrong here. So to do that, what we shall do is we shall pick up one pixel here, say which is black, and note down the coordinates. I note down the coordinates. It is 638, 8, 3, 61, 658, sorry, 658 and 361, and we see that the color is black. So we go to shader and hit shader debugging, and then plug in the coordinates which I noted down, that is 658 and 58, and these are actually the screen pixel coordinates. And as I was showing you earlier, first the region shader invokes and then shoots a ray using the VP inverse matrix. It calculates the ray direction and then shoots a ray, and we see that the region hit the deer because I selected the pixel where we hit the closest we hit the geometry. So if you see okay, let's see what's going wrong here. So okay, before that, in rasterization, we bind the UV buffers in the IA layout, and then a rasterizer interpolates it for us, and we directly get the interpolated UV coordinates in the pixel shader. But here in the closest shader, when you shoot a ray, the GPU quickly figures out which triangle it hit, where and that we get the triangle index in the as a primitive index, meaning which triangle in the geometry it hit, and within the triangle, where did it hit. We get that as built-in triangle intersection attributes, such as a barycentrics. We get the barycentrics here. Now, what do we do? We do a set of computations to access to act to find our goal finally here is to sample the texture at the correct sample the texture and provide the texture value correctly. For that, the additional things we have to do here is bind the index buffer as an SRV buffer, and the UV buffer as a VB buffer. So we can see that here in the hit group. We can see that I have my index buffer and my vertex buffer bound. So this is what we access in the closest fit shader. So let's go. Okay, so we know which primitive we hit. That is primitive index in geometry returned by this function. Primitive index is 2222200, and each primitive has three indices. So I multiply and I'm trying to access the index buffer at that offset. So what do we get? We are getting 000. So it's clearly something is wrong. So let's see. The index offset is 6600. And if we go back to the code, we can see how many buffers we have. Where do I bind? So here I make the index buffer. So let's put a breakpoint here and see what is the size, how many elements do I have in my index buffer. So in my index buffer I have only 5382 elements, and I am accessing index offset is 6600. So I'm getting out of buffer. I'm getting out of buffer behavior, and so I'm getting all zeros. If this SRV has been bound as root SRV, then I would have hit a TDR. because for root descriptors we don't have out of bound behavior. And I think I was sitting at TDR, and that's why I switched to descriptor tables instead of root descriptors, so that I can at least get a pixel capture and analyze what's going on. Anyway, so now what's the issue? So I'm hitting the primitive index is 2200, and and we have three indices per primitive, so I multiply by 3 and I'm trying to access index 6600, and that is clearly out of bounds. So the problem here is, if you go back to the pipeline state and see the index buffer, or else, I can show it in my code also. The index buffer view, if you look at the index buffer view, the format is R16 uint, which means it's a 16 byte buffer. But in my shader, we can't access 16-bit values directly, so we need to either do a byte addressable or a uint addressable. So clearly my calculations are wrong, because if we see, two indices are packed into one. We have packed index buffer, and we can't simply multiply and access a large out of bound buffer. So clearly our calculations are wrong. We are getting out of bound behavior, and that is why this part is, if I go to region writes a UV, the output UAV, and that is why this part, did I stop the analysis? Yeah, I stopped the analysis. And that is the reason all this is out of bounds, and I think this is accessing UV00 and nothing is working. So let's try to fix the calculations here. So stop, and this is my close asset shader. So okay, what do I need to do here? So I think the simplest way is, let's calculate the let's see what we need to actually access. So my index buffer has this. So it has 0 and 1 indices like this, and then we have 0, 1, 3 and 2. So if you go back, it'll be easy to visualize in pics, hit group. I will be accessing as 32. Let's not do byte addressable. So 0, 1 and 2. So the 0th primitive should actually access 0, 1 and 2, and the first primitive should actually access from here 1, 3 and 2, right? So what do we need to do? I think I figured out the easiest way would be to do, so we have num indices per primitive, and let's say num bytes per index is 2, so that we can calculate uint the byte offset into index buffer, which is, let's do this, the primitive index in geometry into num indices per primitive into num bytes per index, right? So we have the absolute byte offset into the index buffer. Now we need to calculate two values. The first value is, if I access it as 16-bit index, if I access it as a 16-bit buffer, 16-bit buffer index, then what is the, so I'll just label it as uh, by index accessed as 16-bit or 2 byte, right? 2 byte accessed as 2 byte equal to, now we'll take the byte offset and divided by 2 bytes, right? And now we are actually accessing it as 32-bit buffer. So now what is the index? So uint index accessed as 4 bytes, 4 byte, which is what I need to use to access. I'll that would be byte offset divided by 4, right? Because this is a byte access, and if I access as a 4 byte buffer, it is 4 if divided by 4. Now I need to so if you see they are different, right? For 0th primitive I need to access 0, 1 and 2. For the first primitive I actually need to access this, so we need to conditionally access. We don't need this anymore. Okay, so I'll replace that. So what is the condition? If index accessed as 2 byte is even, then what do I need to access? Okay, now I need to access as 4 byte. Okay, so okay, I think what will I show is, okay, now the first value is here, right? I need to access this even. So I'll just AND it with 0x 1 2 3 4 f f f f, right? And then the second index is indexed as 4 byte, shifted 16 bits, and then end it with 0x 1 2 3 4 1 2 3 4, and then index as just as 4 byte plus 1, and just end it with 0x 1 2 3 4 1 2 3 4. That's a semicolon. Okay, so yeah, so this is accessed as if it is at an even boundary, we access this, then this, and then this, right? Sounds good. Yeah, now if we access at an odd boundary, then what should we do? Index of x, let's take this, and then the odd boundary is this one, so 0 1 2, and first we need to access this, right? So this bit, I should be mad copying and pasting because it is so confusing. Okay, this, and then indi indices dot y equal to, now I need to do an plus 1 because we access 0, this is for the first one, now this, and now plus 1, I just need to access this and this, right? So this is nothing but this, right? Plus 1 and ampersand, and in this says dot z equal to nothing but the first value, but we should just add a plus 1, right? So plus 1, mm, and we should shift it by 16, right? I should shift it by 16, and then this. So okay, so for plus 1 we are accessing first the uh, lowest byte and then the highest byte. So I think this should work. So let us see. I hope it doesn't TDR or something. Okay, the breakpoint. Take off the breakpoint, and we have the deer. Good job. So yeah, it took me a while to get here. One trick which I would do is, when we got the pixel capture, we got a very, when we are doing the debugging, we got a very high value. So one thing I did to ease my debugging was just go back to the build acceleration structure, and where did I build my acceleration structure? Here. And then this is where you describe the geometry. So it just, instead of using, so how many indices do I have? So originally my original geometry has almost 10,000 index count, and I would feel that is very difficult to debug since we have the source code in our control. Just say, just use 3, right? So what is the advantage of reducing the problem set? We have just 3. So we have just one triangle, right? So I'll show you why one triangle is very easy to debug than such a huge geometry. I always like to reduce my problem set intelligently without any side effects. So if we do this, and if we start the analysis, go back to pipeline, because we need to figure out what is the xy I need to enter. So do this, do this, do this, do this, do this. It appears black, but it does have some RGB value, so it is a correct code now. Anyway, so I'm writing down the coordinates 625 and 280. So when I do shader debugging, it's very simple for me because 625, 280, right? Yeah. Then I can just do, if I plug in the values 625 and 280, then if you go to the closest shader, I mean the closest shader, and try to step through, the primitive index in geometry you get is 0 because that's the first one. So then, when I was coming up with this, I I made sure that x, y, z are okay, 0, 1, 2. So I know that for prim index 0, you go back and you go back, uh, back here, go back to the hit group and see the index buffer. And you know that for just convenience, change it to short. You know that it is 0, 1, 2, and you're accessing the correct values. And then post this, you need to index the UVVB buffer also. So now since it's 0, 1, 2, and the indices are 0, 1, 2. So in vertex buffer also, I just need to make sure that these values are correct. So go back to the pipeline state, go to the vertex buffer, change the representation to float 2, and then just look at 0 0.62, 0 0.67, 0 0.63, 62, 62, 64, 63. So 62, 64, 63. So we know everything is working great. So then I fine-tuned everything and then went back and then changed it to the whole thing, and then it I know it will work because I mean I checked for triangle primitive one also because we have two code paths, and then I know it will work. So yeah, good job again. Bye for now.